Welcome to Frontiers of Research. I'm Antoni, and today we're exploring the fascinating world of molecular machines, devices thousands of times smaller than a human cell that can perform controlled mechanical movements. I'm joined by my brilliant colleague Sarah, whose work in supramolecular chemistry has been groundbreaking, and Josh, who brings engineering expertise to help us understand how these molecular scale devices might transform technology. Today, we'll explore how scientists are designing and building functional machines at the molecular level.
Thanks, Antoni. Molecular machines are exactly what they sound like machines built at the molecular scale. But unlike conventional machines made of metals and plastics, molecular machines are constructed from individual molecules designed to move in specific ways when triggered by external stimuli like light, pH changes, or electrical signals. Nature has been using molecular machines for billions of years. Proteins like kinesin that walk along cellular highways, or the ATP synthase that generate cellular energy by rotating like a turbine. What's exciting is that we're now learning to design and build our own synthetic versions with functions that don't exist in nature.
The field really took a major leap forward in 2016 when the Nobel Prize in Chemistry was awarded to Jean-Pierre Sauvage, Sir Fraser Stoddart, and Bernard Feringa for their pioneering work in this area. Sauvage developed ways to link molecules into chain-like structures called catenanes. Stoddart created molecular shuttles called rotaxanes, where ring-shaped molecules move along axles, and Feringa built the first molecular motors capable of continuous rotation. These breakthroughs laid the foundation for what's becoming a revolution in how we think about machines and molecular engineering.
Sarah, what are the key design principles for creating molecular machines? I imagine it must be quite different from designing macroscopic machines.
That's absolutely right, Antoni. At the molecular scale, we're working in a world dominated by random thermal motion. Molecules are constantly jiggling around due to thermal energy. This is completely different from the macroscopic world where inertia and gravity dominate. So, molecular machine design requires harnessing or overcoming this random motion, which is no small feat. We typically use interlocked molecular architectures, components that can't separate because they're mechanically linked, like rings on a chain. Another approach is creating molecules with parts that can rotate around chemical bonds. The key is designing energy landscapes with stable states and controllable barriers between them, so we can reliably switch the machine between different configurations, using external stimuli like light or chemical signals.
I've read about molecular motors that can be powered by light. How do these work?
Light-powered molecular motors are particularly elegant. Bernard Feringa's motors, for example, use molecules with a central carbon-carbon double bond that acts as an axle. When ultraviolet light hits the molecule, it causes a photochemical isomerization, essentially a partial rotation around this bond. This is followed by a thermal relaxation step that completes the rotation. By repeating this cycle, the motor can achieve continuous rotation in one direction. What's remarkable is that these motors can reach speeds of millions of rotations per second. Some designs can even convert this rotational motion into linear movement, creating molecular scale versions of macroscopic machines like cars or windmills. The energy input is simply photons of light, which makes these systems particularly clean and efficient from an energy perspective.
Josh, from an engineering perspective, what are the most promising applications for molecular machines?
The potential applications span multiple fields, Antoni. In medicine, molecular machines could revolutionize drug delivery by creating nanoscale vehicles that can navigate to specific tissues and release therapeutic payloads exactly where needed. In material science, we're seeing smart materials that can change their properties in response to stimuli, self-healing materials, artificial muscles, or surfaces that can change their adhesion or friction properties on command. In computing, molecular machines might eventually form the basis of molecular scale logic gates that could transcend the limitations of silicon-based electronics. And in energy technology, they could enhance solar energy conversion or catalysis by precisely controlling the position and orientation of reactive components. What's particularly exciting is that many of these applications would be impossible with conventional technology. They're not just smaller versions of existing machines, but entirely new capabilities.
Given how incredibly small these machines are, how do scientists actually observe and measure their movements?
That's a great question. Observing molecular machines in action is incredibly challenging because we're talking about movements on the nanometer scale, or smaller. We use a combination of techniques. Scanning tunneling microscopy can visualize individual molecules on surfaces and even manipulate them. Nuclear magnetic resonance spectroscopy can track changes in molecular conformation over time. Fluorescence techniques can monitor changes in the distance between parts of a molecular machine, if they're labeled with fluorescent markers. And more recently, cryo-electron microscopy has allowed us to determine the structures of molecular machines in different states with near-atomic resolution. Often, we need to combine multiple techniques to get a complete picture of how these machines are moving and functioning.
What are the main challenges in scaling up from individual molecular machines to coordinated systems that could perform more complex tasks?
Scaling up is indeed one of the biggest challenges in the field. Individual molecular machines are fascinating, but to perform useful work, we typically need many machines working together in a coordinated way. This raises several engineering challenges. First, there's the organization problem. How do you arrange millions or billions of molecular machines in precise patterns? Self-assembly techniques are promising here, where we design molecules that spontaneously organize into desired structures. Second, there's the communication problem. How do molecular machines coordinate their actions? This might involve designing cascade systems where the action of one machine triggers others. Third, there's the interface problem. How do we connect molecular scale systems to the macroscopic world to provide inputs and extract useful work? And finally, there's the reliability challenge. Individual molecular machines might fail, so systems need redundancy and fault tolerance. These are all active areas of research.
Sarah, you mentioned that nature has been using molecular machines for billions of years. How much are scientists drawing inspiration from biological molecular machines?
Nature is absolutely our greatest teacher in this field. Biological molecular machines like motor proteins have been optimized through billions of years of evolution, and they achieve remarkable efficiency and specificity. We're learning a great deal by studying how these natural machines work. For example, the ATP synthase rotary motor has inspired synthetic rotary motors, and the walking mechanism of kinesin has inspired artificial molecular walkers. But it's important to note that we're not simply trying to replicate natural machines. We're also creating machines with functions that don't exist in nature. And our synthetic machines are often much simpler than their biological counterparts. This is partly by necessity, as we don't yet have the synthetic capabilities to match the complexity of proteins. But it's also by design. Simpler systems are often easier to control and understand. So it's really a two-way street of learning from biology while also charting new territory.
As we look to the future, what are the most exciting research directions that could accelerate progress in molecular machines?
I see several key frontiers. First, there's the energy efficiency question. How can we design molecular machines that convert input energy to mechanical work with minimal losses? Second, there's the challenge of creating more complex hierarchical systems where molecular machines work together in networks. Third, there's the interface with biology. Can we create hybrid systems that combine synthetic molecular machines with biological ones? And fourth, there's the scaling of fabrication. Developing methods to produce large quantities of molecular machines reliably and at reasonable cost. Progress in any of these areas could lead to significant breakthroughs in the practical applications of molecular machines.
Before we wrap up, I'd like to touch on potential ethical considerations. Are there concerns we should be aware of as this technology develops?
As with any powerful new technology, there are important ethical considerations. Most molecular machines are currently confined to research laboratories and pose little risk, but as applications develop, we'll need thoughtful governance. For medical applications, there are the usual concerns about safety, efficacy, and equitable access. For environmental applications, we need to consider potential ecological impacts of synthetic molecular systems. And in the very long term, as these technologies become more sophisticated, there may be broader societal questions about human enhancement or autonomous molecular systems. The good news is that the field is still developing, so we have time to establish appropriate governance frameworks alongside the technology itself.
Thank you, Sarah and Josh, for this fascinating exploration of molecular machines. We've covered the fundamental design principles, recent breakthroughs in light-powered motors, potential applications across multiple fields, and the challenges of scaling up to more complex systems. While practical applications are still emerging, the rapid progress in this field illustrates how chemistry and engineering are converging at the molecular scale to create new possibilities that were once confined to science fiction. The ability to design and build functional machines at the molecular level represents one of the most exciting frontiers in nanotechnology, with implications for medicine, materials, computing, and energy. Join us next time for more explorations at the frontiers of research.